Hello students, today we are going to start a new chapter. Okay, so chapter number 3 and this is lecture number 10. Okay, so today we are going to start the differential equation. Okay, so as you know, this course is about solving differential equations, and we will find the applications. We will start with some application, since as I said earlier, this course is for solving engineering problems, and especially the mechanical engineering problems, and so we will relate this course to the stress analysis or elasticity problem and heat transfer problem, diffusion problem, etc. Okay. So, differential equations, we will first derive it, and then we are going to solve it. Okay. So, let us start with the stress analysis or elasticity. So, 1D elasticity. Okay. 1D elasticity. Later on we will also look at 1D heat transfer, and which is equivalent to actually 1D diffusion. Okay, so you will get the similar differential equation basically. So both have similar differential equation. Okay, even if you write in 3D, there will be similar equation. Okay, so diffusion. So this is what we will study in details. All the three kinds, mostly only these only. There could be some diffusion plus advection. So diffusion plus advection, and all those things we will see later on. Heat transfer also will have a different kind of things, like a convection, like there will be conductive heat transfer, convective heat transfer. Yeah, so conductive heat transfer. So the heat transfer by conduction, and could be convective, so by convection as well, convective heat transfer. Okay. We will not do the radiation heat transfer. This is because it is non-linear, as you know, or as I mentioned, this course is about all the linear problems. Yeah, so this is linear finite element analysis. Yeah, it is not non-linear. Okay. So let us see the 1D elasticity problem. Okay, so this is a 1D elasticity problem. Okay, and what we are going to do is we will solve this kind of problem. Let us say our problem is some bar is like this one, whose area can be varying. There could be some the body force. Okay, so thus what you are seeing is B x is basically the body force. Okay, so body force is force per unit length. Okay, and there could be at the end also there could be a force, right, and at x equal to 0 or anywhere there could be a boundary condition as well. So here we have u 0 equal to 0, and you have f at x equal to L is some f naught given, or is equal to f naught. Okay. So this kind of problem where this is the what the problem setup is. Area of cross section could also be there. So, we can have A x equal to area of cross section, which may be varying, yeah, which may be varying with x. So, A is not assumed to be constant, it can vary with x, you know. So, that is why A is a function of x, yeah. Similarly, you can have even E, Young's modulus as well, E x, right, Young's modulus also, which may be the may be a variable. So, there could be a Young's modulus which also be changing with length. So, here Young's modulus will be different, here it will be different, here different, here cross sectional area also it could be different here. Yeah. So, we are making a general purpose derivation so that you can use it. So, Bx body force is also there. So, body force, what is body force? Body force is some you can relate it as, let us say you have a bar which is hanging, right. So, this is a gravity like, right, and you have like this, then what happens? It will have a body force, yeah. So, if your x is goes like this, yeah, from here downward, so your body force will be simply rho times. So, let us say at this point if you want to body force, okay. So, body force will be, let us say area is A. So, A x, so area is A x or this is dx, one slice we are taking. So, total volume dV will be nothing but A x times dx, yeah. So, and then mass for this one becomes dm equal to rho times dV will be equal to rho A x dx, okay. So, that is a dm and the force will be equal to nothing but the F dF will be dm times g will be simply equal to rho A function of x then g dx, and Bx which is the body force will be nothing but dF over dx, okay. So, and which is equal to rho z Ax, right. So, this I am giving you just one example, actually it is not that we have to write Bx exactly like rho g Ax. This is one example when you are hanging on a bar from the top, you know. So, and this gravity is downward like this. So, then there will be a force per unit length developed because of the gravity, which you call it a body force. So, it is like you will have a some kind of a force which is giving its tension basically. So, because of its own weight it will be stretched downward, right. So, this is because of the body force. You have not applied any external force at the end, but still there will be a force which will be because of gravity, because of its mass, which will be distributed over it, and we call it body force. So, this is what the body force is. Not necessarily this is because of its self weight, this could be because of many other things. Maybe this bar is in magnetic field, for example, and because of this there may be magnetic pull because of this magnetic field, and this pull may be written as Bx body force, yeah, so which will be dF over dx. Okay. So, now that we are clear about the problem, what we want to solve it, in order to solve this problem, what kind of problem? We have a bar which have varying cross sectional area, which has varying material Young's modulus, along the length, okay, and it has one of the end fixed, at least one of them fixed, and it has some body force. There may be at the end also there may be some force applied. Now we want to find out the stresses, right. Finally, the elasticity problem has objective of analysis of S, means finding out what is the stresses or a strains developed, or what is the reaction force here developed. So, all those things we have to find out. Okay. Now, in order to find out, as I said earlier, we are going to derive differential equation. Okay. So, for the same problem, if we take a slice from here, yeah, somewhere we are going to take a slice, yeah, and a slice will look like this. So, something like this. So, this is one slice we have taken like this, yeah. Okay, and let us say its width is dx, then there will be a sigma here, right. In fact, we can write sigma times A, which is the force here, yeah. So, we write sigma times A. So, where sigma is the normal stress, okay, and okay, I think we should not assume this to be compressive. So, let me do like this. Okay. So, we are assuming it to be tensile. So, we have F equal to sigma times A, and here we will have F equal to sigma A plus d sigma A divided by dx multiplied by dx, right. That is what we will have. So, okay. So, here the force, the pull is sigma times A, here force is we can write probably like this, F1 is like this, F2 is like this. Okay. So, here at one end force is F1, the other end force is F2 equal to sigma A plus d sigma A dx multiplied by dx, and also there is a Bx, right. So, we have the Bx as well. So, which is a force per unit length. So, total force because of the this will be because of the body force will be Bx multiplied by dx will be the total force. Okay. Now, we can write the equilibrium equation, right. So, it could be equation of equilibrium, Okay. So, summation of all forces in x direction has to be equal to 0, and we can write accordingly. So, we have simply that really means is minus F1 plus Bx multiplied by dx plus F2 is equal to 0, or it will be minus sigma A, right, plus Bx dx plus sigma A plus d sigma A divided by dx times dx equal to 0, or what we see here is we have minus sigma A here, we have plus sigma A here. So, they cancel out, and what we have simply is Bx times dx plus d sigma A over dx, right, times dx. So, we this cancelled out already, then we have this term among which dx and dx again cancels out, both them have dx. Yeah. So, what we have is Bx plus d sigma A over dx equal to 0. So, that is what we will get. So, we get d sigma A over dx plus Bx equal to 0. So, this is what our equation is. Okay. So, we get a differential equation here. Yeah. So, but still so this is a differential equation, no doubt. Only thing is we are not going to find sigma directly. Yeah. Or rather we can say this is one of the equations we have a couple of more equations that we have to relate. So, this equation let us have call it number 1, and this equation is also known as the equilibrium equation, right. So, this is equilibrium equation. As I said earlier, so all the differential equations that we are going to use here are coming from some kind of law basically. Either it will be the conservation of energy, as we will see in the heat transfer problem. Here it is the force, the equilibrium of force basically, that based on that we have derived. Similarly, in case of diffusion, it will be conservation of charges, so, or the species. So, whatever is coming to a volume and has to exit from that volume, right. So, same kind of thing, because it is in equilibrium steady state we are solving, right. So, this is the equilibrium equation that we get from here. Okay. Now, the thing is, as we have seen earlier, we have solved for force and displacement. So, in this equation we do not have any displacement yet. So, we have to find out some displacement, and how to find out? Okay, so, we have to write some kind of relationship, use some kind of relationship that will tell us how this sigma is related to displacement. Yeah. So, we will also known as a stress. Finally, we have to, from a stress we have to convert into displacement. Okay. So, we have to think. Okay. So, first thing it comes to mind is sigma. If we know sigma, we can find out epsilon, right. So, like epsilon is nothing but a strain, and a stress equal to E times epsilon. So, sigma equal to E times epsilon, where E is the Young's modulus. So, here we get epsilon, but now we know that epsilon is equal to du over dx. So, that we have to use two relationships. So, I am going to write that. So, we have to, second what we have to use is Hooke's law. Okay. And what is Hooke's law? Hooke's law says sigma equal to E epsilon. Okay. So, but we have assumed that E is a function of x. So, we will raise sigma equal to E x times epsilon, right. So, this is number 2 equation, and third equation is what is known as the strain displacement relationship. Strain displacement relation, right. And this one will tell us this epsilon is equal to is du over dx. Yeah. So, this is third one. So, this tells you how the what is the rate of change of displacement, or rather if you have a bar like this one. So, u2 minus u1 divided by L will give you the displacement, as we have done in case of in the programming, you must have seen that. Yeah. So, in the direct method also we try to find out the strains, and what we did, we find out what is the displacement at one end and what is displacement at the other end. We took the difference and divide by the length, right, whatever total length is. So, yeah. So, that gave us actually du over dx basically. So, that is what it is. Yeah. So, now we are going to combine 1 and 2 and 3. So, 1 plus 2 plus 3 gives us nothing but, so we have this equation. So, we will write d over dx. Okay, that's right. Let us write it. So, d over dx, and then bracket, and then we have sigma times a. So, a is a function of x actually, as we have written here. A is a function of x, E is also a function of x, B is also a function of x. So, accordingly we will write all those things. So, this should be sigma a is a function of x. where sigma itself is equal to Ex times Ex. Ex is a function of x times E, where E is a function of du over dx. Yeah. So, if you combine them together, what we will get is simply this Ex times Ax times du over dx. Yeah. So, this is what you will get, okay, plus Bx equal to 0. Yeah. So, this is the differential equation, finite differential equation that you get. Yeah. So, we have combined all the three relationship. So, what we will see is this epsilon is equal to du over dx. So, you have du over dx. This epsilon, which is du over dx multiplied by Ex, this multiplied by Ex is nothing but the stress sigma, and this sigma multiplied by A is nothing but the force, right. So, sigma is this, okay. So, this sigma multiplied by this area is the total force and the resulting force, right. So, okay. So, and we have this differential term here plus Bx equal to 0. So, this is what our differential equation is. Now, in order to solve it, you also need some boundary conditions. So, in boundary condition plus boundary condition. So, you have to write plus boundary condition, right. So, differential equation is not just one equation, it also comes with boundary condition, so that you can solve it, so that it has a unique solution. So, boundary conditions. So, we have to see the boundary conditions. The boundary condition will be given, will vary problem to problem, but one thing we want to see is what is known as essential boundary condition. Essential boundary condition, right. And this is the meaning that if you have a we have to define the, in this case the boundary condition on displacement u. Yeah. So, meaning that if your equation has this term where you are differentiating u with respect to s, this you must have a boundary condition on u, and this is essential. Yeah. So, that is why the essential boundary condition, you need to say u equal to 0 at x equal to L or x equal to 0, right. So, you have to tell, or you have to say u equal to 5 at x equal to 0, those kind of things you have to tell. So, you have to apply, there must be at least in one D problem, there must be at least one boundary condition, only one, at least one the essential boundary condition. Okay. So, this is what that is, right. So, okay. Then next is what is called in natural boundary condition. So, natural boundary condition. Okay. And what is the meaning of that? This is the boundary condition of force term basically, right. So, this is the boundary condition on the derivative of u, that is basically force. Yeah, that is force equal to what? Sigma times A, and where sigma is what? Sigma is E times del u over del x. So, basically here in this case basically when you say E A, yeah, and du over dx is nothing but force only. So, if you have a boundary condition on force which is proportional to the derivative of displacement, then you call it it is a natural boundary condition. If you do not give, if it is a by if you are providing natural boundary condition, if you are providing, you need to provide only when it is not equal to 0. Yeah. So, by default this will be equal to 0 only. Yeah. So, by default natural boundary condition equal to 0 unless you provide, meaning that what is the meaning of that? Okay, so let us see here. So, let us say you have a problem the same as we have taken, and you have a body forces like this one. Now, what happens is you have this body forces here. Now, either you will let us say here if you apply a force here, then what we will do? You are going to say at this point EA times du over dx at x equal to L is equal to f naught, right. That is what we will write. Yeah. If you do not write, that really means that f equal to 0. Yeah. So, if it is given, if it is given, f naught is given, we write what will. So, let us say f naught is given, and then let us write the differential the boundary condition to begin with. Your first boundary condition is u at x equal to 0 is equal to 0, because we have fixed, and this will be the essential boundary condition. Now, f naught if you are giving, then this will be the natural boundary condition. So, you will write E A du over dx at x equal to L equal to f naught. Yeah. So, this will be the natural boundary condition. Yeah. Now, if you do not apply any f naught, then you do not have to write E A times du over dx at x equal to L equal to 0. You do not have to write, because it is understood. Yeah. So, unless you are applying a load, you do not have to actually say there is no force here, because automatically it means there is no force. Yeah. So, actually there is no force here. If you look at the outside, like we have only two boundary, either you have this boundary and this boundary, right, as far as this is concerned. So, boundary condition either force will be here or here. So, if the force is there, you will say this equal to the force. If there is no force, you will not say that this is equal to 0. It automatically it means, and in that case all the stress analysis will be based on the body force only. Okay. Anyway, so far we learnt about the differential equation for the stress analysis problem for 1D elasticity problem, and now once we have the differential equation, next job is to solve it. Okay. Now, how to solve it? Now, solving you can have many ways. One will be the direct method, right. Direct method means you integrate it, right, and we will use maybe we should solve it to see the what really is the solution looks like, and so that we can also compare with other solutions. Other solutions means approximate solutions that we will also solve. Okay, we will also obtain it. So, let us say our problem is simplify it further. We will take circular cross section, area we will take as a constant. So, we take Ax equal to A naught only. So, constant, and then length we have L, and then Ex is equal to E naught only. So, E naught is also constant. Then we have Bx, we may not have that, okay, we do not need to have. So, or okay, let us have that, I think so that we can find out at least the general purpose solution for that one. Okay. So let us say Bx again is B naught is a constant force per unit length which is being applied. If that is the case, our equations here becomes simply d over dx and E naught A naught du over dx plus B naught equal to 0, or it will be E naught A naught d square u over dx square, okay, plus B naught equal to 0. So, this is what equation is. Let us say there is no other things there, meaning that you can write the boundary conditions as well, boundary conditions, and what is that? We have x equal to 0 here, this x equal to L. So, we have u at x equal to 0 is equal to 0, and we have E A means f equal to E A du over dx at x equal to L. No, okay, we do not have anything like that. So, we will not write anything, maybe we do not write anything like that. Yeah. So, okay. So, this is how it is given basically, and we are going to find out solution based on that. Yeah. Okay. If that thing is given, then we can integrate, simply we can integrate and we can find out the solution. So, we have like this, right. Okay. So, how will you do? So, we can simply have integrate here and we can find it out. So, we have d square u over dx square is equal to minus B naught over E naught A naught, and that tells us that u will be equal to minus B naught over E naught A naught, and then you integrate once and you will have x, term here, next x term here, and then you will get a constant C1, let us say. So, if du over dx will be what? Will be equal to minus B naught over E naught A naught multiplied by x plus C1. Now, you integrate again. So, this becomes u will be equal to x square, 2 term here, plus C1x plus C2, that is what it will be. So, I will write directly here. So, minus B naught over E naught x square over 2 plus C1x plus C2. So, this is what the solution of u is. Now, we have to apply the differential equation, the boundary condition here. Yeah. Okay. Okay. Remember that we are solving it just like you solve any differential equation. Yeah. So, we are not applying any finite element analysis yet. We are just solving so that later on we can compare with what we have obtained, like this one. Yeah. Okay. So, we have this one. Now, we can apply the boundary condition here, and accordingly we can find out. Yeah. Okay. Now, at the when we put x u equal to 0, at x equal to 0. So, you put 0 equal to x equal to 0, x equal to 0. So, what we get is C2 equal to 0 simply, right. So, then apply the boundary condition. We say apply the necessary boundary condition. Apply the essential boundary condition. okay, and then what we get? We get 0 equal to C2, or basically C2 equal to 0, we get that. Okay. Okay, now if we have that, the okay, so in this equation we have C2 equal to 0, rest is like this one. Yeah. Now it also at the end, if you see, there is no stress, right, sigma. So basically the when in the finite element analysis, when we will do it, we will see that we actually do not need to mention that we do not have to write in terms of the in terms of boundary conditions. Yeah. So meaning that we do not have to write at the end we have E A times del u over del x equal to 0. Yeah. So by default it is assumed it is 0 only, and if there is a load applied, then we apply a load. Okay. But since we are solving it as in differential equation, and in that case we know that the order of differential equation is 2, and hence we will need two boundary conditions. So one boundary condition is what is essential boundary condition, and second boundary condition is the force equal to 0 at the, so force at x equal to L equal to 0. So this is the natural boundary condition that we apply here. In any case, we need the two boundary conditions for solve a differential equation of order 2, right. So this will be, here we have to apply because we are solving the differential equation like we are integrating, hence we will need it. However, in the when we have the matrix form, when we apply a finite element analysis, there we do not have to apply, automatically it is assumed equal to 0. If there is a force applied, then you have to enter that force equal to this. Okay. And the way you also did in the by solving the truss also. So wherever the force is, you put the force, otherwise there is no force, then you put 0, right. So like that. Okay. Now here the when you apply the natural boundary condition now. Okay. That really means what it tells you is du over dx equal to 0 at x equal to L. Okay. I am saying this one because force is equal to 0, and force is nothing but Ea times du over dx is the force. So if Ea times du over dx is force, and that is equal to 0, hence du over dx is also 0. Yeah. So when we what is du over dx? Du over dx is nothing but means du over dx equal to minus b naught over e naught a naught, and then we have x plus c1, right, plus c1, okay, is equal to 0. This now, since du over dx equal to 0 at x equal to L, so that really means 0 equal to minus b naught over e naught a naught, and then we have x equal to L plus c1. That tells us that c1 equal to nothing but b naught L over e naught and a naught. Okay. So we got the value of c1, and hence we can write the finite value of u will be minus half b naught L not L, b naught over e naught a naught x square, right, plus b naught b naught L over E naught A naught times x. So, this is what we get finally, this is what we get. We get u equal to minus half b naught over E naught x square plus b naught L over E naught A naught times x. So, this is C basically, C1x. So, this is the answer. Okay. Okay. So, here the if you put x equal to 0, you get u equal to 0. If you put x equal to L, so what you get here? You get b naught L, then L over 2, and here you get L square. So, they will this and this will be 0. Yeah, so d over dx will be 0 at x equal to L, right. So, this is the solution you get. Okay. So, this is the exact solution. I will rewrite here, and we will see what is the meaning of that. So, we get u x equal to minus b naught over E naught A naught, and then we have x square, we have 2 here, plus b naught L over E naught A naught times x. So, this is u basically, and if you plot it, how should it look like? You can have like this. You have x like this, and u is 0 as x equal to 0, yeah, and then you can also have the x, this is a combination of x multiplied by this minus b naught over 2 E naught A naught x basically, right. Okay. So, the slope, just looking at it like from point of view of a mechanical engineer, how will it look like? It should be here there will not be displacement, yeah, and displacement will be highest here, of course, because this is at the end. So, the highest displacement should be at this end. Displacement is positive. Also, what we see here is the slope of the displacement. Also, we can see. So, the displacement here, if you see displacement of here and here, will not be much different. Okay. So, this will be here. If you look at this point, for example, there is no force at the end, and the slope should be 0. Okay, du over dx should be 0 here. Yeah, so that means it should have something like this type thing, right. So, no force. So, our diagram should go something like this one, like this. Yeah. Okay. So, this should look like something like going like this. Yeah. Why? Because the u, here we have u basically. So, we have u x equal to 0 here, and the slope will be maximum here. Slope will be maximum means force will be maximum, meaning that the force will be maximum means axial force, the normal force will be maximum, and that is true. Force will be maximum there because here if you cut here, for example, you will see the force due to all of them integrated. If you cut it here, you will have only this force, total force divided by area will be the stress, or force will be just summation of all these body forces till here only. If you cut here, summation of all body forces till here will be the normal force, and so on. So, hence you will see what? You will see the slope here should be the maximum, and slope here should be 0, and in between it will be, the slope will be linearly changing. Yeah. Okay. So, hence you are getting like this one. Yeah. So, slope here is a maximum, and n it is changing, and at the here it will be 0. Okay. Okay, so this is how it will looks like, and now we are going to solve it different methods. Okay, so this is the exact solution. We say this is the exact solution. Okay. You can also find out what is the force at the other end, what is the reaction force here. Yeah, that will also check whether our solution is correct or not. Our force here should be equal to all the body force multiplied by L. So, B naught multiplied by L should be the force here, and it should be negative. So, let us see whether it is correct or not. So, we have du force, as we know, is equal to E A du over dx, and we have means E naught A naught multiplied by minus B naught over E naught A naught x, right, plus B naught L over E naught A naught. Okay. So, f at x equal to 0 is equal to nothing but minus B naught. Okay. So, not minus, let us see here, when x equal to 0 we are talking about, right. So, we have x equal to 0 here. If you put like this, x equal to 0, then what do we get? This term becomes 0, and what we get is plus. Yeah. So, we get plus B naught, okay, plus B naught times L. Just let me write it nicely. So, we get B naught times L. However, as I said earlier, the force should be negative. Why is it coming positive? Yeah. So, we are getting f equal to E A multiplied by d du over dx as positive number here, but if all the forces are this direction, here we expected force has to be negative. So, that is in the negative x direction and negative x direction. Okay, this is because if you see here our derivation, if you see, okay. So, if you see our derivation, we have drawn here f1 equal to sigma a, and here f2 equal to sigma a like this. So, our this is at this end, a force in negative x direction is the positive one, right. So, that really means if you are getting any value f equal to B naught times L, B naught times L, which is, so whatever your value you are getting, that indicates that positive value will tell you that at the left end the direction is in the negative x direction. Yeah. So, from here, from the derivation, you have to look at the derivation, how you, what you assume it to be positive. So accordingly you have to interpret. So, that tells you that the whatever your value is getting is if value B naught times L, if you are assuming it to be positive, means all the forces be in this direction. So, at this end a positive value will indicate that force in the negative x direction, and hence negative or positive you have to always relate to your derivation in while derivating what you assume to be positive or negative accordingly. So, at f x equal to 0 equal to B naught L, if you are getting, then you are saying that you will write that f naught equals to this, you look at towards negative x direction. Right? So, we will write the interpretation rather than writing minus B naught L, you can also write we are getting this force, but this is towards negative x direction. Okay. So, accordingly it will the meaning will be clear. Okay. Now, this is what the exact solution looks like, and you can find out the stress from here. So, if you want to find out sigma, sigma will be nothing but as you know, this is simply E times del u over del x will be the sigma, right. So, E times du over dx, which will be simply from here if you look at this. So, sigma will be the E times du over dx. So, there is no a term there. So, you remove a naught, you will get that. So, without a naught you will get the stress term. Yeah. So, we can write E naught multiplied by minus B naught over E naught A naught x, yeah, plus B naught L divided by E naught A naught. Yeah. So, you got that. So, anyway, so we have solved all of the things. You can find out a strain. The strain is nothing but du over dx simply. So, further if you remove E naught from here will give you the strain. So, from here to here a strain term is there and multiplied by Young's modulus is gives you the stress term. So, everything is known so far. The thing is, our aim is to find out approximate solution. Okay. So, the aim of this course is find out, aim is to find out the approximate solution. Okay. And how to find out, that is the main thing. Yeah. So, it is right now we have integrated. The problem is in a complicated problem we may not know the exact solution. A complicated problem could be something like this one. Yeah. So, let us say we have one dimensional bar only, but we could we can have this kind of okay. So, our bar is not regular, for example, then we may have E bx which will be complicated, it is not constant, but it could be of any type, right. Could be bx equal to maybe 1 minus e to power minus alpha x kind of thing, could be like that, divided by, it could be even divided by beta plus x as like this one, maybe complicated so that we cannot integrate it, right. So, maybe of x square, maybe even more. Similarly, ax could also be some a lot of complicated things, right. So, 1 over gamma plus delta x square, let us say this is also given, and we can have log xi plus x, yeah, making all kinds of things is possible, right. So, if you make this complicated, yeah, you can have area which is a complex term, or the body force which is a complex term, and you try to integrate, you will have very difficult time, you know. So, in that case you can assume some solution and you go from there. Okay. So, what kind of solution you assume? So, this approximate solution you do for a complicated problems, and in that case you are assume some solution. Okay. So, you assume some solution, and what kind of solution you assume? Polynomial solution, right. Polynomial is the polynomial solution is very popular solution, but very easy to work with, and hence we are going to assume some polynomial solution. And why? Because it's easy to work. You can also choose a piecewise polynomial, meaning that if you have a problem which is a bar like this one, you will assume one polynomial from here to here. Let us say we are divided that into several part, so maybe you have 0, x equal to L over 4, x equal to L over 2, x equal to 3 all over 4, x equal to L, and then you are assuming one polynomial from here to here, the second polynomial, third polynomial, fifth one, third one and fourth one, a piecewise, right. So it could be also piecewise, and that can be a number of polynomial can actually find out solution which is approximate solution, but it may be the close to the exact solution. Yeah. So this is what why it is important that you find out the approximate solution, and our choice could be polynomial solution, which is very easy to work with, and we will see that why it is so easy. And there are many methods for doing it, and that's what we will be working on in the next lecture video. So we will start with some kind of some methods. We will see like which methods have been used to find out approximate solution, and those approximate solutions finally led everything to finite element analysis. So we are not exactly getting into finite element analysis, but finite element analysis will come later on. So right now we are just looking at like how initially, before developing a finite element analysis, how people solve approximate solutions, how they obtained it when they saw the problem was difficult, and then they had to come up with some approximate solution, then what strategy they used. And if you understand that, automatically it will be easy for you to also understand the finite element analysis. Okay, so that's what we will do next time. Okay, that is all for now.